Hello everyone, welcome to the second week's problem solving session for the course Fundamentals of Food Process Engineering. So if you guys can hear me, please let me know, and if you can see the screen. Okay, so in this class we will be taking up problems related to the syllabus of week 2. So in this in this week, we majorly had topics discussing about the viscoelastic nature of the fluid. So we'll start with the questions. So these questions are majorly theory-based questions. So if you guys have any doubts, please stop me there. You can post it in the in-call messages so that I can answer your questions. If you want me to repeat any topic, kindly let me know. So these are just theory-based questions, so we'll be able to finish off the class pretty soon. Okay. So question 1. Which of the following viscometer is based on the principle of Stokes' law? A. Cup and bob viscometer. B. Falling sphere viscometer. C. Cone and plate viscometer. And D. Rotational viscometer. So if you guys know the answer, kindly post it in the in-call messages. If you guys have any doubts or want me to repeat anything, please let me know. So any clue what the answer is? So before that, can anybody tell me what a viscometer is? Okay. Viscometers are instruments that are used to measure the viscosity of a liquid. So that liquid need not be a Newtonian liquid. The liquids can be basically anything, and viscometer helps you to figure out the viscosity of that particular liquid. So there are different kinds of viscometers based on the kind of fluid that you're trying to measure. So there are some that are specifically for Newtonian fluids, some that are for a mixture of both Newtonian and non-Newtonian fluids as well. So in this case, which of the following viscometer is based on the principle of Stokes' law? So if you before that, we need to know what Stokes' law is. Yeah, the answer is B. The Stokes' law is the basis of a falling sphere viscometer in which the fluid is stationary in a vertical glass tube. So for those who have attended the previous problem solving session, what a falling sphere viscometer was described in the previous session itself. I'll describe it anyway now. So in a falling sphere viscometer, you will have a vertical glass tube that is stationary, and you will have a fluid filled in it, and a sphere of known size and density is allowed to descend through the liquid. That is, the top part of the cylinder will be open, you will put a ball through it, and the ball will now descend through the liquid. So if correctly selected, it reaches a terminal velocity which can be measured by the time it takes to pass 2 marks on the tube. So you'll have a marking at the top of the cylinder, you'll have a marking at the bottom of the cylinder. So when the ball first reaches the top marking, you'll start the timer, and when the ball reaches the bottom of the second marking, you'll stop the timer and calculate how much time it has taken for the sphere to pass from point A to point B in the cylinder. And with that, you can calculate the viscosity of the fluid, which is actually related to the time taken by the sphere to pass between two specified lines on the cylindrical tube. Okay, so based on the liquid, So if the viscosity of the liquid in the tube is high, the time taken for the ball to pass will also be higher. So if the viscosity in the cylinder is high, then the time taken for the ball to pass from A to B will also be high. If the viscosity is low, then the time will also be less. So the velocity of the ball passing through the cylinder is indirectly proportional to the viscosity. So the answer is option B. Any doubts in this? Okay, moving to question 2. The Deborah's number is represented as A. The characteristic time period of a material by frequency. B. Characteristic time period of a material by time period of observation. C. Time period of observation by characteristic time period of material. And D. Frequency by characteristic time period of a material. So before we go into this question, are you guys familiar with the concept of viscoelasticity? So what is the difference between a viscoelastic fluid and a viscous fluid? So in a viscoelastic fluid, the fluid will have both the characteristics of a viscous fluid as well as an elastic solid. So in an elastic solid, the moment you apply stress, immediately the strain will also increase. So it's basically like an elastic rubber material that you guys already understand, and an elastic material follows the Hooke's law. So if you guys have gone through the week 1 lecture, you will know what a Hooke's law is. So Hooke's law, does anybody know what Hooke's law is? Any clue what Hooke's law states? Okay, Hooke's law states that the stress applied to an elastic object is directly proportional to the strain. So stress is directly proportional to a strain for an elastic material. The moment you apply stress to an elastic material, you will automatically see an increase in the strain as well. And how is it different from a viscous material? In case of a viscous material, the stress is directly proportional to the rate of strain, not strain. It is proportional to the rate of strain. I hope the difference is clear. In case of an elastic fluid, stress is directly proportional to strain. In case of viscous fluid, stress is directly proportional to the rate of strain. So a fluid that has both the viscous properties as well as elastic properties are known as viscoelastic fluids. So generally Deborah's number is used to represent or basically give an idea of the nature of these viscoelastic fluids. So any clue what a Deborah's number is? Or any clue what the answer to this question is? Okay, so there are different kinds of viscoelastic fluids based on how much viscous it is or how much elastic it is. So some materials can have more elastic nature and less of viscous nature. Some materials will have more viscous nature and less of elastic nature. So different materials will have different variations in the amount of elasticity and viscosity. So based on that, Deborah's number will change for that particular fluid. So Deborah's number basically gives you an idea of whether a viscoelastic fluid is more viscous or more elastic in nature. So that is the function of a Deborah's number. And when you go by the definition, let's say when we look at a graph here, this is a graph of stress versus time, and this is a graph of strain versus time. So in case of an elastic material, you can see if you have given a stress at some, say, sigma at time t equal to 0, you give a stress for a constant time and then you release the stress. So this is what you're doing to a material. So if it was an elastic material, you will have the exact same graph for strain as well. The moment you give stress, you will see an increase in strain. As long as you hold the stress, you will have this strain also. And the moment you leave the stress, the strain will also automatically drop. So had it been an ideal elastic fluid, you will have the same graph here. Stress versus time will look the same as strain versus time. But since now it is a viscoelastic fluid that you're dealing with, what happens is at time t equal to 0, when you give an initial stress here, you will have a sudden increase in strain till here. This is because of the elastic property of the viscoelastic fluid. Then when you keep holding on the stress, you will see that the strain gradually increases instead of saturating throughout. So this is because of the viscoelastic behavior of the fluid, because it has both viscosity as well as elasticity. And then when you drop the stress, you don't see an immediate drop in the strain as well, but you see the strain gradually decreasing in kind of an exponential manner. So this is known as the relaxation time. The moment you drop the stress, this is not the relaxation time, the process is known as the relaxation. So the moment you drop the stress, you do not see an immediate drop in strain, but you see a gradual decrease in the strain. So this is the characteristic graph of a viscoelastic fluid. So in this case, Deborah's number is a dimensionless number often used in rheology to characterize the fluidity of material under specific flow conditions. So Deborah's number is basically relaxation time or characteristic time period of the material divided by time period of observation. So relaxation time in this particular part of the graph, here you can see that the moment you drop the stress, since you drop the strain gradually decreases. So the time where the stress is now 36.8% of the strain, that is known as a relaxation time. We'll discuss what relaxation time is in more details in the upcoming slides. But as of now, what you need to know is that Deborah's number is relaxation time divided by time period of observation. So I'll tell you what it means when Deborah's number is less than 1 or when Deborah's number is greater than 1. So answer is option B here. We'll discuss this in more details in the upcoming slides. Okay, question 3. If the relaxation time of the liquid is less than the characteristic deformation time, then Deborah's number is less than 1 and the fluid appears to be more viscous than elastic. Deborah's number is greater than 1 and the fluid appears to be more viscous than elastic. Here Deborah's number is less than 1 and the fluid is more elastic. And Deborah's number is greater than 1 and the fluid is more elastic. So you have two conditions here. You need to first figure out if the relaxation time is less than the characteristic deformation time. What is Deborah's number and what does it mean? This is the basic question. So for that, we'll first understand. I'll show you a slide here where you'll be able to better understand what is happening. Okay. So just look at this graph here. Let's say you have a viscoelastic fluid and you give it a certain strain. So you make sure that a certain strain is maintained in that fluid. Some kind of deformation is kept constant. So the strain you have suddenly increasing at time t equal to 0. You are maintaining a strain throughout at epsilon naught. So this is your deformation that you are applying on the fluid. So what happens to the stress is that instead of increasing and maintaining constant like an elastic material, you will see a sudden increase at time t equal to 0. So sigma is the stress here. This is the strain versus time graph. This is the stress versus time graph. So you can do both. You can either keep the stress constant or you can keep the strain constant. That depends on the kind of test you are running. We'll discuss that later, but here in the previous graph that I showed you, we were maintaining the stress constant. Here we are maintaining the strain constant. Either ways you can use to describe a viscoelastic fluid. So in this case I am keeping the strain constant, and here you can see that at time t equal to 0, the moment you increase the strain, you see a rapid increase in stress. So this is because of the elastic nature of the fluid. Then even though you are maintaining a constant strain, you can see a decrease in the stress, which means that in a viscoelastic fluid, if you want to maintain a constant deformation, the amount of stress you need to apply keeps on decreasing with time. It gets more easier to maintain that strain in a viscoelastic material. Had it been an elastic material, you would have to apply the same stress throughout, which is your stress versus strain graph, stress versus time graph, and strain versus time graph will look exactly the same. Because it's a viscoelastic fluid, the amount of stress that you need to keep on maintaining the strain drastically reduces with time. Is this part clear? Is this getting confusing? If you guys want me to repeat in a more simpler way, please let me know. It's basically, you can imagine a roti dough or something where you can keep applying a particular strain to it, and over time it becomes easier to deform the dough. Like same way how you are kneading the dough in chapati and all, the slowly it gets more easier to mix the dough or deform the dough. So that dough, chapati dough, is an example of a viscoelastic food. So over time it becomes easier, or that is, you need lesser amount of stress to maintain this strain. So here you can see that the stress is slowly decreasing with time, and the time at which the stress becomes 36.8% of the initial stress. That is, this is the initial stress sigma naught, and it slowly starts decreasing. The time at which sigma is equal to 36.8% of sigma naught is your relaxation time, and that is what is the numerator for Deborah's number. That relaxation time is the numerator for Deborah's number. Let's say this is your relaxation time. Somewhere here is your relaxation time, and this is your Deborah's number's denominator. That is the total time that you are taking to observe the material. Is this part clear? Do you guys remember what Deborah's number is? It is relaxation time by total time. That is Deborah's number. So relaxation time by total time is Deborah's number. So had it been a completely elastic material, what would be your Deborah's number? Or before that, what would be your relaxation time? If you have a completely elastic material, will your relaxation time be very high or will it be very low? So if you're able to understand this, it means that you have understood the concept of relaxation time. Relaxation time is the time at which your stress has decreased by 36.8% of the initial stress. So had it been an elastic material, what would have been your relaxation time? Would it have been very high? Would it have been very low? So since an elastic material does not decrease at all, elastic material will stay the same like this. Your stress versus strain graph will look the exact as your stress versus time graph will look exactly the same way as your strain versus time graph, which means that your stress will never drop at all. If your stress never drops, it means that you have an infinite amount of relaxation time. You keep waiting and waiting and waiting, the stress never drops to 36.8%. Is this part clear? Why relaxation time is very, very high for an elastic fluid? In case you guys don't understand, please post it in the in-call messages. I'll repeat it again because this is a bit tricky or a confusing concept. But once you understand this, it would be easier for you to go with the next questions. An elastic material's stress versus time graph will look exactly the same, which means there will be no drop in the stress at all, which means you won't be able to observe a relaxation time. The stress will not drop to 36.8%, which means you will have to use up infinite amount of time to even see a drop in the first place. So for an elastic fluid, relaxation time is very, very high. Whereas in case of a completely viscous fluid, no elasticity or anything, the moment you apply stress, it will start flowing and you don't need to apply stress anymore. So for a viscous fluid, relaxation time is very, very low. So do you know now, can you understand the difference now between elastic fluid and viscous fluid? Elastic fluid has very high relaxation time because there is no drop in stress. Viscous fluid will have low relaxation time because it has a very, very rapid drop in stress. So given that condition right now, so now you'll be able to answer this question better. If the relaxation time of the liquid is less than the characteristic deformation time is basically the total time of observation. So your Deborah's number is basically relaxation time of the liquid divided by the characteristic deformation time or time of observation. So if this is less than the characteristic deformation time, then it means that Deborah's number is less than 1. That is, if numerator is less than the denominator, your Deborah's number is less than 1. In that case, what does it mean? If your relaxation time is very less than the time of observation, then it means that the fluid appears to be more viscous. Only elastic materials have very high relaxation rates. Only viscous material have low relaxation rates. So since relaxation rates of viscous fluid is very less, Deborah's number is also less and hence fluid appears to be more viscous. Basically, to sum up, the Deborah's number represents the ratio of the duration of the fluid memory to the duration of the deformation process and used as a measure of viscoelasticity. So if Deborah's number is less than 1, that is, if the relaxation time of the liquid is less than the characteristic deformation time, the fluid appears to be more viscous than elastic. On the contrary, if Deborah's number is greater than 1, it appears to be more elastic than viscous. The answer here is option A. Is this part clear? What Deborah's number means, what relaxation time means, and what does it mean to be more viscous or more elastic? Because this part of the viscoelasticity is the topic that has been discussed in 3 out of 5 lectures. So you need to understand properly what it means. Is there any doubt? Some kind of an answer would be helpful. Is it okay to proceed? Is it not? Okay, I'll proceed with this. In case you guys have doubts, just ask me. I'll repeat the part again. Question 4. In the dynamic test for a real material, it will have a phase shift between A 45 degrees and 90 degrees, B 0 and 90 degrees, C 30 and 60 degrees, and D 60 and 90 degrees. So before we go into it, do you guys know what a dynamic test is and what is it used for? What is a dynamic test used for and what does it involve? Okay, so as I said, to measure the viscoelasticity of a material, you have multiple tests. One was the one that we saw here, that is maintaining a constant stress and finding out what the strain is with respect to time. This is the creep test. Okay, so this is one kind of a test to find out what viscoelasticity behavior of the fluid is. This is known as creep test, where stress remains constant. And then you have stress relaxation test. Yeah. Then you have stress relaxation test, where you maintain the strain constant and you measure the stress with respect to time. These are two tests, and third test is the dynamic test. So there are three tests for viscoelasticity. One is stress relaxation test, second is creep test, and third is dynamic test. So dynamic test is what we are going to discuss right now. So in the dynamic test, what happens is you give a sinusoidal stress to the material. You either give a sinusoidal stress or strain to the material and accordingly calculate the other part. So if you are giving a sinusoidal stress, you measure the strain with respect to time, or you give a sinusoidal strain and you measure the stress with respect to time. Basically the concept is you are giving something sinusoidal in nature. Okay. So in a dynamic test, the material is subjected to sinusoidal stress or strain, and the strain or stress response is measured. So if you are giving stress, measure the strain. If you are giving strain, measure the stress. In either case, it is a sinusoidal nature. So let's say we are giving a sinusoidal strain to the material. So in that case, this is how a sinusoidal function looks like. Gamma is equal to gamma dot gamma 0 sine omega t, where gamma is your strain at any point at time t, gamma 0 is your amplitude of the sinusoidal wave, and then you have omega t, sine omega t for your sinusoidal nature. Okay, so let's assume that you are giving a sinusoidal strain to the material. So then as you remember in my previous slide that I told you, for an elastic material, what is the stress proportional to? Is it proportional to the strain, or is it proportional to the strain rate? What is an elastic material stress proportional to? Yeah, elastic material's stress is proportional to the strain. Whereas in case of a viscous material, the stress is proportional to the rate of strain. Okay, so we already know what the strain is. So your stress is going to be proportional to this for an elastic material. For a viscous material, we need to find out what is the rate of strain. So for that, we differentiate this equation with respect to time. So then you have gamma dot, which is basically d gamma by dt with the rate of strain. Then you have gamma 0 dot, and then when you differentiate sine omega t, you get omega cos omega t. This is basic differentiation of sine x. So you have, when you differentiate this equation, you get gamma dot equal to gamma 0 dot omega cos omega t. So cos omega t can actually be written as sine omega t plus 90 degrees. This is 11th standard maths, if you guys remember. So now we know that for an elastic material, stress is proportional to the strain, which is this. For a viscous material, stress is proportional to the rate of strain, which is this. So now, if I am giving a sinusoidal stress to an elastic material, my stress equation will also look exactly the same way. There is no phase shift here. There is no omega t plus something. It is basically omega t plus 0 degrees. Is this part clear? So your elastic material will have 0 degrees phase shift. So let's say this is a graph of a completely elastic behavior material, and I'm giving a certain stress, so I'm giving a certain strain, and my stress will look pretty much exactly the same way. There will be no shift in the strain or the stress. Okay, so this is for an ideally elastic behavior because your stress is directly proportional to strain. In case of a viscous behavior, my stress is proportional to the rate of strain. So here you have sine omega t plus 90 degrees, which means you have a phase shift of 90 degrees. So if you start giving strain right now, you will be able to see the sinusoidal nature of the stress only 90 degrees after. So there is a phase shift of 90 degrees. So this is for an ideal elastic behavior. This is for an ideal viscous behavior. And now, since dynamic test is done for viscoelastic nature of the fluids, to understand the viscoelastic nature of the fluids that have both viscosity and elasticity, it will have a phase shift between these two. It will have greater than 0 degrees and less than 90 degrees for a real material or a viscoelastic material. It will neither be ideally elastic, it will neither be ideally viscous. So it will have something in between these two, which is 0 degrees and 90 degrees. So the answer to this question is option B. Similar to in this case, this is the graph of a viscoelastic behavior, where the shift between the two waves, the stress and the strain wave, is between 0 and 90 degrees. Is this part clear? Why for elastic it is 0 and why for viscous it is 90? Okay, so this is the third kind of test that we use to understand the viscoelastic behavior of the fluid. So based on the angle of shift also, you can say how viscous it is or how elastic it is in a viscoelastic behavior. Okay, moving on to question 5. In which model is a spring and dashpot connected in series? So before this, are you guys aware of the different kinds of models that are used to describe viscoelasticity? In case if you guys had the time to go through the week's lecture, you would know, but are you aware or should I explain? Because the rest of the questions are majorly dependent on the model here. Okay, so in order to describe the viscoelasticity, so we learned the different kind of test for viscoelastic behaviors. So apart from this, if we want to model a fluid flow somewhere, we need to know, we need to develop a model for that kind of a fluid. So different kinds of models were developed to describe different kinds of viscoelastic fluids. So there were, those are the kind of models that we'll be discussing right now. So you have in each of these models, you will have a spring and you will have a dashpot. Okay, so spring is basically giving you spring is representative of an elastic behavior. You give a stress that is proportional to the deformation, that is directly proportional to the strain in a spring. So the spring represents the elastic behavior of the fluid. The dashpot is basically you have a pot with a piston in it, and that pot is filled with fluid. So when you push and pull it, basically you're dealing with a fluid here that is completely viscous in nature. So a dashpot is basically a pot with a piston and fluid filled fully in it. Spring will give you an idea of the elasticity behavior of the fluid. So you have spring and dashpot to describe elastic and viscous nature of the fluid. Yeah, so you have spring and dashpot, which will each describe one particular behavior of the fluid. Now, how this is being, how the spring and dashpot are arranged will give you different kinds of models. So some models will arrange it in a series, some models will arrange it parallelly, some models will arrange it in a combination of series and parallel methods. So each of these models best describe certain classifications of viscoelastic fluids, which is what we will see in the upcoming questions. So in case of the spring represents the elastic nature of the fluid and follows Hooke's law, which is also the case of an elastic solid. The dashpot represents the viscous nature of the fluid and follows Newton's law of viscosity. The dashpot is basically like this. You have a piston, you have a cylinder with a piston in it, and this will be filled with a fluid of viscosity eta. And this spring will have a Young's modulus of E, capital E. So when you have a when you are describing a fluid with a certain model, you will have different arrangements of these spring and dashpot. So in this case, you have first a spring, which is then connected to a dashpot in series, and then you apply some force at one end. Let's say you apply force on one end, so you will have that force traveling through the elastic part of the series and the dashpot part of the series as well. So this model is known as the Maxwell model and was one of the first models developed to understand the viscoelastic nature of the fluid. One of the first, or rather the most simplest model used to describe the viscoelastic nature of the fluid. So this is Maxwell's model, spring and dashpot connected in series. Okay, we will discuss the rest of the models in the upcoming questions. I hope this is clear what spring indicates and what dashpot indicates. The answer is option C here. Moving to question 6. So here we will discuss each and every model in detail. So A, you have Maxwell's model. In list 1 you have Maxwell model, Kelvin model, Berger model, elastic model and viscous model. And in list 2 you have spring and dashpot in series, combination of Kelvin and Maxwell model, spring and dashpot in parallel, and 5 dashpot. So with the given information in the previous slide, can you solve this question? We already know 3 of the answers. So what does A correspond to in the list 2? Are you able to understand what these models are for? A, okay, C is your answer. A corresponds to 2, B corresponds to 4, C corresponds to 3. B corresponds to, yeah, so the answer is C. So we'll, A corresponds to 2 in this case. So we'll first solve what we already know. A will correspond to 2, which is what we discussed in the previous slide. D corresponds to the spring. The elastic model is described best by a spring that follows the Hooke's law. So D corresponds to 1, and viscous model corresponds to the dashpot, which is the cylinder with the fluid in it with the specific viscosity. So now Kelvin model as Maxwell model, I'm just basically repeating what I said here. Elastic and viscous components are represented by spring and dashpot respectively. So and Maxwell model is used to interpret the stress relaxation of viscoelastic liquids, especially polymeric liquid. So Maxwell model was initially first developed to describe polymeric liquid, and in this case your two elements, that is the spring and the dashpot, is connected in series, and the total shear strain can be expressed as the summation of strain in the spring and the dashpot. So this is an important line here, because this will vary according to different models. The total strain, let's say you're pulling one end of the spring, the total, you will have some deformation in both these places. You will have an elongation of the spring, you will have the piston moving up and down. So in both these cases, and because of the piston moving up and down, you will see a deformation in the fluid inside the dashpot as well. when you're pulling apart. So you will see a deformation in both these regions. So the total shear strain can be expressed as the summation of the strain in the spring and the strain in the dashpot. So gamma spring plus gamma dashpot is equal to gamma total. This is for Maxwell model and strictly for Maxwell model. For Kelvin model, it will change. So we'll discuss Kelvin model. In Kelvin model, the creep behavior can be described by Kelvin-White model. This model also contains a spring and a dashpot but connected in parallel. So here you can see this is Kelvin model. Instead of connected in series, it will be connected in parallel. In this case, the strain will be equal. When you pull apart here, both these will experience the equal amount of strain. But the stress will be summed up. So here gamma of spring is equal to gamma of dashpot, but tau is equal to tau of spring plus tau of dashpot. Is this clear? In this previous case, tau is the same for both. Tau of spring is tau of spring is equal to tau of dashpot equal to tau, but strains are summative. Here it's the other way around. For Kelvin model, strains are the same, stress are summed up. So in a Kelvin-White model, you see both a kind of a mixture of different kinds of this thing. So you have an elastic material, you have an elastic spring, you have a dashpot connected in parallel. This entire stuff is again connected to a spring here. So different models will describe different kinds of fluids. So when you are doing some kind of a modeling, you will need to check which kind of model best describes your fluid based on the kind of data that you have. So this is Kelvin model, this is Kelvin-White model. And Berger model, so Berger model was developed because Kelvin model was not able to explain all the fluids, or most probably food kind of materials was not being described by the Kelvin model. It was able to describe fluids but not the food materials. So Berger model was developed, which is a combination of the Kelvin model and the Maxwell model. So here you have the Kelvin model. If you can see, if you can remember here, this is the spring and dashpot connected in parallel, and then you have a spring and dashpot connected in series also. So this is Kelvin model, this is Maxwell model. Together this is known as the Berger's model that combines both. So the answer here, as you guys said, it is option C. Hope this is clear. Different kinds of models. Moving on to question 7. The rotational viscometer is suitable for the characterization of dash and time dependent behavior. You have A elastic, B non-Newtonian, C Bingham, and D none of these. So before we answer this question, do you guys know what a rotational viscometer is? Any examples of rotational viscometer that you guys know? So as the name suggests, in this rotational viscometer, you measure the viscosity of a fluid in a container where at least one part is moving or rotating. So you learn different kinds of viscometer. You already know what is a falling ball viscometer that we discussed in the first question and in the previous class. The other kind of viscometer is a rotational viscometer. So rotational viscometer can be of two types. You have coaxial cylinders and you have a cone plate system. So in case of a coaxial cylinders, you have, as the name suggests, you will have a cylinder within a cylinder with different radiuses, and between these cylinders, that is in the annular region, you will have your fluid whose viscosity you want to measure. So between the cylinders you will have the fluid, and you will rotate either the outside cylinder or you will rotate the inside cylinder, either ways. This is a coaxial cylinder measure viscometer. In case of a cone plate viscometer, you have a plate here, and you have a uh, cone shaped instrument here. So between the plate and the cone, you have the fluid, and this angle is actually very minute. The angle between the cone and the plate, that is this angle, is very minute, and in that minute region you will fill the fluid whose viscosity you want to measure, and you will keep rotating the cone, and based on different forces that act on the fluid whose description is described in the lecture videos. You guys can go and look into those description and the derivation. If you guys have any doubts, you can post it in the discussion forum and we'll take it up at that time. So basically one of the parts will be rotating, and for these you can see that these are not these rotational viscometers can be used for both Newtonian and non-Newtonian fluids, especially the shear thinning kinds. Because this is a very small region in between, a shear thinning fluid is much more preferable, because the more and more shear you give, the viscosity will decrease, so it will be easier to rotate. If you give a very extremely highly thick fluid or so, the rotation will itself become very difficult. So shear thinning fluids where the viscosity decreases over time is kind of preferable, and there are two reasons why rotational viscometer is very useful. First, because you can control the amount of strain that you give on these. You can control the amount of shear stress that you give on these fluids based on the angular velocity of this rotation. So if you rotate very fast, you can give more stress. If you rotate very slow, you can give less stress. So the amount of stress that you give on the fluid can be controlled by the rotation speed. So the shear rate is directly proportional to the rotational speed of the system, so that you can control. The shear rate can be controlled. Second thing is that you can keep rotating it for as long as you want. So you can do a time dependent study as well. So this viscometer is also used for time dependent fluids, that is the rheopectic and the thixotropic fluids. So these rotational viscometers have two purposes. One is to control the amount of shear rate that you give, and second is to study the time dependent behavior. So both can be done with these rotational viscometers. So the answer here is you can study non-Newtonian fluids, especially shear thinning fluids, and you can study the time dependent behavior of the fluid. But one thing that becomes difficult is, since the region between these are very small, there is a good chance that the temperature would be very difficult to control. You'll have a lot of shear, you'll have a lot of friction that will increase the temperature of the system. The moment temperature increases, your viscosity no longer remains constant. It will keep changing with respect to temperature. So maintaining constant temperature is a challenging part in these viscometers, but it is very important to maintain the temperature in order to get accurate measurements. Is this clear? Am I going too fast? If you guys want me to slow down, please let me know. Okay, moving to question 8. What value of angle alpha is between the cone and the plate in the cone and plate viscometer? So more than 3 degrees, more than 5 degrees, see less than 5 degrees and less than 2 degrees. So we just discussed what a cone and plate is. You have a plate, you have a cone, and you have a fluid between the cone and the plate. So what should be the angle between the cone and the plate? It's not B right now. It should be, the angle should be very less. So you're not looking at more than 5 degrees. You are looking at less than 5 degrees. So the value of angle alpha, I'm not sure if this. So this is this angle is known as alpha between the cone surface and the plate. So this angle is known as the cone angle, and that should be less than 5 degrees in a cone and plate viscometer. and we make sure to maintain a smaller angle because smaller the cone angle, higher the achievable shear rate. You can have a wide range of shear rates, ranging from a low to a very high shear rate if your angle remains small. There are often cone plate viscometers with angle less than 3 degrees also, but generally we have less than 5 degrees. So the answer is option C. Okay, moving to question 9. Which of the following statement is incorrect? So this is something that you guys might be aware of by now. 1. The falling ball viscometer is suitable for low viscosity fluids. 2. The force exerted on the ball is only gravitational force. 3rd, the net force is gravitational force minus buoyancy force plus drag force. 4. The wall effect is undesired in the viscosity measurement. So just imagine what a falling ball viscometer is. This is something that we discussed in the first slide and in the previous class. So which of these we'll go with the first statement. Falling ball viscometer is suitable for low viscosity fluids. Is it correct or not? C is not the answer. We'll go one by one. So falling ball viscometer. If you had a viscometer with extremely high viscosity, will it be suitable or not? If you have a long cylinder with extremely viscous fluid and you drop the ball on one end, the ball will not even fall. It will take a long time for the ball to pass from one position to another position. So a falling ball viscometer is not suitable for high viscosity fluids. It is in fact suitable for low viscosity fluids. So statement 1 is actually true. So we'll go to the second statement. Force exerted on the ball is only gravitational force. So if you drop a ball in the liquid, how many forces are involved? When a solid item is passing through the liquid in a vertical direction, there are 3 forces involved: buoyancy and drag, which acts in the upward direction, gravity, which acts in the downward direction. So the force exerted on the ball is not only gravitational force, there are 2 other forces involved. So statement 2 is false. That is one of the statements that we identified. Now third statement, the net force is gravitational force minus buoyancy force plus drag force. So is that net force equation correct or wrong? Based on the direction of the force that I just discussed, what should be the answer? Statement third is false, because if your ball is dropping like this, you have gravitational force acting downwards, drag force and buoyancy force acting upwards. So the net force is gravitational force minus buoyancy force minus drag force. So this should be minus. So statement third is also incorrect. And fourth, wall effect is undesired in viscosity measurement. What do you mean by wall effect here? And when does it happen? So what happens if you have a long cylinder like this and you pass a very big ball almost close to the radius of the cylinder? What will happen is there's a good chance that the ball will hit the walls of the cylinder, or the walls will start to slow down the ball. So apart from these forces, you will also have the effect of the wall or friction or something of that sort because of the walls of the cylinder. not because of the fluid. So if you have a very big ball, it will keep touching the walls of the cylinder, and that will also have an opposite direction force. You don't want that. You want your measurement to be strictly due to the fluid present in the cylinder and not because of the wall of the cylinder. So, which is why when you select a ball, you select one with a very small diameter. That is one of the main constraints in this experiment or in this method of viscosity measurement, where your balls will be of known density and will be small enough so that it does not get dragged by the walls of the cylinder. This is known as the wall effect. So wall effect is undesired because it will add to an additional force, and whatever you measure will not be due to the fluid, it will be because of the fluid as well as the cylinder wall. So wall effect is undesired in a viscosity measurement. So statement 4 is true. So only 2 and 3 are wrong. The falling ball viscometer experiences 3 forces, and the net force is equal to gravitational force minus drag force minus buoyancy force. So the answer is option A. Moving to question 10. In a Kelvin-White model, the total shear stress is caused by the deformation is dash, and all the strains is dash. So if you guys remember what a Kelvin-White model is it series or parallel? Kelvin-White model, the spring and the dashpot is connected in series, or is it connected in parallel? So in a Kelvin-White model, you will have the Kelvin model has a spring and a dashpot connected in parallel. So in this case, your strains so your strains will be equal to each other. That is, total strain is equal to strain in the spring equal to strain in the dashpot. This is for a Kelvin model. Whereas the stresses will be the summation of the individual stresses. So tau is equal to tau spring plus tau dashpot. This is for the Kelvin model. So basically your strain can be, if you consider a parallel unit, you can consider strain as your voltage, stress as your current. So in a parallel model, your current will split, whereas your voltage across the parallel unit will be the same. So similar way. So your strain will remain the same, the stress will be the summation. For a Maxwell model where the spring and the dashpot are connected in series, it is the other way around. Your current or the current or the stress will be the same. Your strain or the voltage will be different. I hope this is clear. So the answer is option A. The total shear stress is caused by the summation of the individual stresses, and all the strains are equal to each other. So apart from the arrangement of the spring and the dashpot, these are the things that majorly differ between the Kelvin model and the Maxwell model. Moving to question 11. Which rheological model is most suitable for a biological material? We have A. Kelvin model, B. Maxwell model, C. 3-element model, and D. Berger model. So this is something that I discussed in the previous slides. Which of these models best describes the real food materials? So Maxwell model was the one in series, Kelvin model was the one in parallel, and Berger model is the combination of these Kelvin and Maxwell model. So Kelvin model does show excellent retardation, but it is not the case in many foods. So Kelvin model does model a lot of viscoelastic fluids, but when it comes to food, Kelvin model kind of lacks precision. So Berger model is proposed, which is a combination of Kelvin and Maxwell model. You will have both parallel and series, and that is suitable for biological materials. So answer is option D. If you guys remember what a Berger model is, this is how a Berger model looks like. You will have both parallel and you will have series. Okay, so Berger model, since it combines both the features of the Kelvin model and the Maxwell model, it is able to describe food materials much better than any of these models. Okay, so we have an equation here for strain. Epsilon at any time t, which is a strain at any time t, is equal to sigma naught by E naught. Sigma is the stress, capital E is the Young's modulus of the spring. So sigma naught by E naught plus sigma naught by ER into 1 minus exponential of minus t by lambda retardation plus sigma naught t by mu naught. So I'll tell you what is what here. Epsilon is the strain, sigma is the stress, capital E is the Young's modulus of elasticity for the springs, lambda ret is the retardation time, and mu is the viscosity of the fluid that is present in the dashpot. So what do you think this equation is related to? And which term corresponds to what? So when you're talking about a model, the model needs an equation, right? So this equation corresponds to which of the models? The answer is right here. The Berger model, which is a series combination of Kelvin and Maxwell model, in which the total strains are summed up. The strain is equal to summation of the first term, second term and the third term, which I will explain what it is right now, where lambda retardation is the retardation time for the Kelvin part of the model. Okay, so in this case, let's look at the first term, that is sigma naught by E naught. E naught, this term is for the spring that is outside the parallel, that is the spring of the Maxwell part of the model. Spring outside the parallel system is what is described by this first term. The last term describes the dashpot outside the parallel unit, which is described by mu naught or viscosity in the present in the dashpot. The second term, you can see it has a combination of both. It has a combination of both for the elasticity and the viscosity of the fluid. So lambda retardation comes when retardation times come for viscous fluids and viscoelastic fluids. For elastic fluids, retardation time is infinite. So when you talk about relaxation or retardation time, it comes only for viscoelastic fluids, which means that the second time in the combination describes this parallel unit. Is this clear? The first term sigma naught by E naught is to describe the elastic part of the outside spring. Sigma naught T by mu naught describes the dashpot outside the parallel unit. The second term describes the entire parallel unit. And as you can see here, the strains are a summation of each and every strains. So this is a concept of Berger model. In Berger model also, your strains will be equal to the summation of strains because it is a combination of both Kelvin and Maxwell model. So you'll have features of the Kelvin model coming in and you'll have features of the Maxwell model coming in. So in Maxwell model you had the stress same and the strain summation. So since it has a combination of Maxwell model, you again see a summation of the strain. You will also see a summation of the stress, but that is not a part of your course right now. So we are not discussing about stress here. The equation that has been described in the video lectures is given here. So the answer is option D. I hope this is clear. Okay, question 13. In a parallel plate viscometer, statement 1, there are two parallel plates where one is rotating and the lower plate is fixed. Statement 2, the upper plate is circular and rotating while the strain is offered to the liquid which is kept between the plates. Which of these statements is true? Which of these statements are false? Okay, this is how a parallel plate viscometer looks like. Here you have two parallel plates. It can either be circular or it can be rectangular in shape. The shape is fine, but here we are looking at a circular parallel plate. So you will have liquid filled between these two plates. The standard concept of a viscometer is you will have two surfaces and liquid filled in between them. So in this case you have two parallel plates. You will have a liquid filled between these parallel plates and the top plate will be rotating and the bottom plate will be fixed. So this is what happens in a parallel plate viscometer. So statement 1 is true. But when you come to the statement 2, the upper plate is circular and rotating while the strain is offered to the liquid which is kept between the plates. So this is false because you are not offering stress. The top plate rotating results in a shear. You are not offering strain, you are offering stress. It occurs in a shear stress. That's the difference. You are trying to maintain a certain shear stress and you are not offering a shear strain. Hence statement 2 is false. Answer is option C. Is this clear how a parallel plate viscometer works? So the all the formulas for each and every viscometer is described in the lecture videos. I recommend you guys go and look into those lecture videos and the formulas to have a better idea of what is happening. Here we are just talking about how the instrument setup is and what is happening. So question 14, example of Weissenberg effect is A jellies, B oil, C fruit juice, D bread dough. Before we proceed with this, does anybody know what Weissenberg effect is? You guys would have actually experienced it in your daily life. What a Weissenberg effect is? So it's also known as the rock climbing effect. So if you take water in a beaker or in a vessel and you continuously stir it, you see this kind of a vortex forming. That is a downward side vortex. This happens for Newtonian fluids, which is water. When you take non-Newtonian fluids like bread dough or so, if you knead a bread dough, you will actually see it rising up. So this is known as the rock climbing effect or the Weissenberg effect. This is because when you are trying to stir it, you are trying to disrupt you're trying to deform the particles. You're trying to disrupt the molecular arrangement of the particles in the fluid when you're stirring. Now, had it been only a viscous fluid, it will look like this. You will be able to successfully deform the particles. Now, since in viscoelastic behavior of the fluids, you have an elastic component also, the moment you give some kind of a stirring speed, the particles will try to get back to its original position because of the elasticity. You will try to give it a stirring speed, there will be some kind of a deformation, but at the same time you will also have an elastic behavior which will try to pull the particles back to its original position. Now, since you have both kinds of properties, both viscous and elastic properties, what will happen is you will have one force acting in this direction, one force that is trying to get back because of elastic nature. So because of this, what will happen is there will be a resultant force acting upwards. Because of the elastic nature, you will have a backward effect that will result in a net force acting upwards, which means now the particles will start climbing on the rod, on the steering rod, because of the elastic nature of the fluid. So this is known as the rod climbing effect. So you give a stirring speed to disrupt the molecular arrangement of the particles, but because of the elastic nature, the particles will tend to go back to its original position, and in that process you will actually have a net upward force that results in the rod climbing effect or the Weissenberg effect. So this happens in case of viscoelastic fluids. If a rod is rotating in the viscoelastic fluid, instead of being displaced out by the motor by the centrifugal forces, it begins to climb around the rotor because of the net upward force. So this is known as the Weissenberg effect and is applicable for viscoelastic fluid, which in this case is bread dough. The rest and all, if you mix, you will actually have a material like this. Yeah, so the answer is bread dough. So hope you guys understood what Weissenberg effect is. You'll be able to see it in your daily life if you try to knead your bread dough or cake batter or something with a kneader, with the instrument. It will try to climb on top of your kneader. Question 15. In a viscoelastic material, the stress required to maintain a certain strain is A, independent of time, B, decreases gradually over time, C, increases gradually over time, D, first increases and then remains constant. So imagine a bread dough or a atta. So what will happen? The stress required to maintain a certain strain is independent of time, decreases, increases, or first increases and then remains constant. So we have been discussing that in terms of relaxation rates and stuff. Why will the stress increase? Imagine your chapati dough or something itself. You know, kneading it over and over and over and over, does it become easy or does it get difficult to maintain the same amount of stress? Yeah, it gets easier. So your stress that is required to maintain the certain strain will decrease gradually over time. This is what we've been discussing as relaxation times. For when we were discussing Deborah's number and all, we were discussing about relaxation times where the stress was dropping. So the stress required to maintain a certain strain will decrease over time. So let's say at time t0 we give a sudden strain and we maintain that strain throughout. So in a viscoelastic behavior, you will see a sudden, you will actually see a first sudden increase because of the elastic nature of the material, and then you will start to see that the stress slowly decreases because of the viscous nature of the material. It has both elastic and viscous nature. So this part is because of the elastic behavior, this part is because of the viscous behavior. So you will see that the stress slowly drops even though you maintain a constant strain. So this is exploited in a stress relaxation state. So the answer is option B. Is this clear? And when I meant first increase, it's not, we are not talking about an instantaneous increase here, which is why it does not, yeah. So it does increase, and then but it's an instantaneous increase. You won't be able to quite measure it, but then yeah, it's an instantaneous increase, and then it decreases gradually over time. It does not remain constant. Had it first increased and remained constant like this, it would have been similar to an elastic behavior. The answer is option B. Is this clear? The same will happen if you have the stress also. If you give a sudden stress also, the strain will keep on decreasing for the sudden, strain will keep on increasing for the sudden stress, for the same amount of stress. We'll discuss that. So this is what is known as stress relaxation test, where you're measuring the stress relaxation. This is known as the relaxation. You're measuring the stress relaxation at a constant strain. So this is the stress relaxation test, or the one of the tests that is used for viscoelastic behavior. We already discussed what dynamic test is in one of the previous slides, where you have a sinusoidal nature. This is the other stress, that is the stress relaxation test. Strain is constant, stress keeps relaxing, and you're measuring the relaxation of the stress. Question 16. Relaxation time. This is something that we're discussing again, just in case if you guys didn't understand previous time. The relaxation time is observed when the stress reaches dash of the initial stress. So here I'm giving an instantaneous strain. Again, this is the example of a stress relaxation test. Strain is constant. So I'm giving a constant strain. I'm measuring the stress relaxation, which comes out like this. So you see that my stress slowly gradually drops. So let's say how do I measure what the relaxation time is? So let's say when the time, the numerator here, is equal to the relaxation time here, which is tau. So this equation is basically sigma equal to sigma naught exponent of t minus tau. This is t naught because you are having it here. If your t naught was 0, this will be exponent of minus t by tau. So for now, for simplicity, let's assume that t naught is equal to 0 seconds. So this entire equation will go into sigma equal to sigma naught exponent of minus t by tau, where sigma naught is this initial rise. Here this is sigma naught, and tau is your relaxation time. So now if I substitute t as tau, what will be my sigma? So when I substitute t as tau or tr, I'm mentioning it as tr, but I'm substituting it as tau or the relaxation time. So now it becomes sigma equal to sigma naught exponent of tau by tau, which is 1. Sorry, minus 1. You have minus t by tau. So it will become minus 1. This is clear. T naught goes to 0. T, we are substituting it as tau. So you have sigma equal to sigma naught exponent of minus 1, which is basically this. And 1 by E is 0.368. So your sigma is equal to 0.368 of sigma naught. That is when T is equal to tau. So the answer is option A. So when your stress keeps on decreasing, the point where your stress has now become 36.8% of your initial stress, that corresponding time is known as the relaxation time or tau. Is this clear? The derivation? Assume T naught as 0 and at t equal to tau, you have sigma equal to sigma naught exponent of minus 1, which is sigma equal to sigma naught by E. 1 by E is 0.368. So sigma is equal to 0.368 of sigma naught, which is 36.8%. So this is how you measure the relaxation time. And again, for a viscous fluid, relaxation time is very, very less because it will immediately drop. For an elastic fluid, it will have the same graph as this, which means it will never drop, which means your relaxation time will be infinite. I hope this is clear. Based on this, your de Broglie number will also change. Question 17. Statement 1. Thixotropic fluids show decrease in viscosity but increase in shear stress with time. And statement 2. Bentonite clay is an example of thixotropic fluid. So which of these statements is true or false? So what is a thixotropic fluid? Okay. So we'll discuss the answer. Thixotropic fluid, we'll see if the answer is B here. So thixotropic fluids show decrease in both shear stress and viscosity at a constant shear rate over time. So it is where the viscosity and the shear stress decreases with time. It's not just one decrease, both of them decrease with time, and hence statement 1 is false. Statement 2 is also false because bentonite clay becomes more harder. It's clay. So bentonite clay becomes more viscous or more resistant to flow over time. Hence it is actually rheopectic. Rheopectic is the opposite of thixotropic. Thixotropic viscosity decreases over time. Rheopectic viscosity increases over time. Since we are dealing with clay here, bentonite clay is an example of rheopectic fluid, not thixotropic fluid. So statement 2 is also false. Answer is option D. So this is the graph between shear stress and time. For Newtonian fluid, at a constant shear rate, you will have the same kind of shear stress. Whereas in thixotropic fluid, the stress will decrease, viscosity will also decrease. Rheopectic fluid, stress will increase, viscosity will also increase. So moving to the last question, I think, question 18. The results of the creep test are given in these form of parameters: A. Compliance, B. Shear rate, C. Uniaxial compression, and D. Viscosity. So creep test, do you guys remember what creep test is? We discussed previously in the same session. There were 3 kinds of tests for viscoelasticity: stress relaxation test, dynamic test, and creep test. So in creep test, what remains constant? Does shear stress remain constant or strain remain constant? So the stress relaxation, in the case of a creep test, stress will remain constant. It is the exact opposite of a stress relaxation test. Here you will keep the stress constant. So you let's say instantaneously you are increasing the stress, and after some time you are removing the stress. So you will measure what the strain is with respect to time. So here, when you immediately increase the stress for a sudden period, for a short period of time, you will see a sudden increase in strain as well. This is because of the elastic nature of the material. And then after a while, you can actually see a gradual increase in the strain. This is because stress is directly proportional to the rate of strain in case of a viscous fluid. So you will have the viscous fluid will start dominating, and you will see a slow increase in the shear rate till your stress is maintained. So this part is because of the viscous behavior of the fluid. Then once you drop the stress, you will have a sudden drop in strain also. This is again because of the elastic nature, and after a while you'll see a gradual decrease in the strain, which is because of the viscous nature. So both viscous and elastic behavior will keep playing around. Every time you give a stress or you remove the stress, you'll have a sudden increase or decrease. Then you'll have the viscous nature coming in. So because of the viscoelastic behavior of the material, the strain will not completely go to zero at all times. You will actually have some kind of strain remaining, some permanent deformation remaining. This is because of the viscous nature of the fluid. Had it been completely elastic, your strain would have dropped to zero. It will be like a spring. The moment you remove the force, it will go back to its original position. But since your viscoelastic fluids have a viscous part also, it is not necessary that the strain will go back to zero. You will have some kind of a permanent deformation throughout. So this is how your creep test looks like. In your stress relaxation, this was the only part that was there. You had a sudden increase and you had a drop. In creep test, this is how your graph looks like. But the results of the creep test are given in the form of something known as compliance. You will not get it in the form of shear rate or uniaxial compression or viscosity. You will get a graph as compliance versus time, where compliance is strain by stress. It is like the opposite of viscosity. Viscosity is stress by strain. Here creep compliance is strain by stress. So when you get the results of the creep test, you will get it as compliance versus time, where you will be having information from both the strain as well as the stress. The answer is option A. So with this, we conclude the problem solving session for this week. Do you guys have any doubts in any of the questions that we've discussed? Anything that needs to be repeated? So majorly you need to understand the different techniques used to study the viscoelastic behavior, the stress relaxation test, dynamic test and creep test. Then you have different models for describing the viscoelastic behavior. That is the Berger model, Maxwell model, Kelvin model. And then you have different types of viscometers. You have the falling ball viscometer, you have the rotational viscometer, you have the plate viscometers. So these three are the main topics for this particular week. Apart from that, you have other topics as well, but these three are the recurring topics from this week syllabus. Yeah, PPT will be provided. I will immediately upload it right now. So within another half an hour, it should be available on NPTEL for you guys. The PPTs of week 1 have already been uploaded. I hope it is accessible to you guys. The recording has also been uploaded in YouTube. In case you guys missed the class, you can go through the recordings as well. This week's recording will be uploaded soon.